Hello everyone. As you know, lectures 13 and 14 won't be included in your final exam. Let me check if there's a technical problem or not. No, it's okay. So, but as you know, trees are very important because the applications can be found in many fields, including computer science, mathematics, statistics. So you see trees almost in any field. So it's important to define it and categorize it anyway. So let's go through this lecture briefly. So what is a tree? Tree is a connected, undirected graph with no simple circuits. For circuits, I will show you in an example. You already know what we mean by undirected graph. It means that you don't have any direction from one vertex to another. It just shows that two vertices are connected. There is no arrow like this on undirected graph. So for connected one, again, it's good that I will show you in one good example. So let's see it in the example that what do we mean by a tree. So we have some graphs here, as you can see. All of them are graphs. G1, G2, G3, G4. Now, one by one, you can check them whether it fits the definition of a tree or not. For G1 and G2, this is the case. This is true. Why is that? Because all of them are connected, undirected, and we don't have any simple circuits. And another way is also to check whether this is a simple graph or not. But not all simple graphs are trees. So again, we should check the other conditions as well. But as soon as you find the counterexample that this is not a simple graph, you would say, okay, this is not a tree. So it shouldn't have a loop, for example, like this. If we have vertices and they are connected and there's a loop, this is a problem, so this is not a tree. Or, for example, from one vertex to another, we shouldn't have more than one edges. So again, this is not a tree. Okay, now let's see why G3 and G4 are not graphs. Because these two, if you check them, you will see that it has all the conditions that we mentioned in the previous slide. But why this one, G3, is not a tree? This is the counterexample. But just a counterexample is good enough to say that this is not a tree. You see, from E to B, and then B to A, then A to D, then D to A, you will see a circle. It means that from one point, you shouldn't be able to reach again to the same point. Like for the previous one, if you consider, for example, D, there is no other path that you can find that again you will reach D. For example, if I connect these two together, then this is not a tree anymore. So what? Now you know what I mean by a simple circuit. From one point, again, you should not be able to reach it back. Otherwise, that's a problem. So for this counterexample from E, you can see that you can get back again to this point. That's why this is not a tree. What about G4? G4 is not connected. Now, this is the best time to show what I mean by connected. It means that all the vertices, there should be a path that we should reach it. So here, as you can see, from D to C, all of them are connected. But here, A to F is connected. It's like these two are two separate graphs, and we just put them together, you see? And that's what we mean by connected. Whenever we see any disconnection, then we cannot see that's a tree. If we had a vertex here, this could be another story, right? But the vertex was not here. It was not defined. That's why this is not a tree. Now look at this theorem. An undirected graph is a tree if and only if it means that this is a bijection, biconditional case, if there is a unique simple path between any two of its vertices. Also, this is a good way to check whether a graph is a tree or not. Or from now on, we could say even a simple undirected graph. So, for example, from this point to this one, there should be a unique path so that we will reach it. And I don't consider, for example, going somewhere and again get back case, right? So if you don't consider that, there should be just a path to reach it. For example, this vertex is not connected to this one, otherwise it was not a tree. You see? Again, you choose any point, and if you want to reach another one, there should be only one path to reach it, without repetition of vertices, of course. So this is a good theorem in order to check whether we are dealing with a tree or not. Because trees are not always as what it looks like, for example, here. It's not easy always to recognize that this is a tree or not. And why this is important? Because when you are trying to design a new discrete computational model, then in that case, you should make sure that what you have designed, for example, is a tree, if that's what you are looking for. So these things we should be careful about. There are different types of trees. Even in the book, it mentioned about so many of them, not only in this chapter, in the previous chapters also, time to time, it mentioned, for example, this is binary trees, for example, and so on. So there are so many of them. But if you want to categorize them, it's possible also to categorize them in rooted and unrooted trees. And what do we mean by rooted trees? It means that it starts with an initial vertex. So this is a parent, as we say in trees. So all of them are the children. So this is the roots, and these are the leaves of that. And sometimes we mention about the endpoints as the leaves of the tree. So these are the leaves. And also we could say, for example, these three are children of this parent. These are some notations that they use often for trees. But when we say these are rooted trees, it means that you should find an initial point. This vertex is the root of this tree. Right away, this is clear. And especially now that this is a directed graph, you can see that. But you know, at the beginning, I mentioned that when we talk about a tree, this is connected and undirected graph. So when you see a tree, you don't see these arrows. So this is not correct to show that. But here in this example, it is shown just to say that this is a direction, okay? Because I could, for example, change the arrow and the direction could change for the root of this tree, okay? Otherwise, we shouldn't put these arrows. So otherwise, I cannot call it a tree. So there are so many applications, as I said at the beginning of the lecture, but I chosen these two because some of you already taken bioinformatics from me, so you already know that trees could be very useful, for example, even for bioinformatics, like this one that we call phylogenetic tree. And we have different species, and we are interested to know which species can be in the same group. And it's not just, as you can see, for example, group 1, group 2, it's not like that. Each one of them can have parent, you see? So for example, here cow and sheep, they are in the same group. And here horse and dog in the same group. We don't know based on which characteristic we are grouping them, but we are trying to find the similarity between the species. So if I say, for example, for a specific gene, this is the diagram related just for that specific gene. So this is the diagram. But if we are talking about another gene, for example, maybe the similarity of human is closer, for example, to cat suddenly. It rarely happens, but it can happen. So these trees can be very useful in order to get us ideas what's going on in terms of grouping. So if I say, for example, based on this tree, is cat more similar to humans or a horse? Or, for example, I could say, for example, which one of these three are closer or similar to each other? So as you can see, the parents of both horse and cat the same here, you see. But for human, in order to reach this one, here is the parent for human comparing to these two. So from here we understand that horse and cat should be in the same group and human should be in the separate group. So trees can be very useful to get us ideas what's going on in terms of put different species, for example, here in the same group or not. And this is just related to phylogenetic trees. We can have several examples in several fields related to trees, of course. And I'm sure you will see many of them in your different courses. So far we talked about rooted trees. Also, we have another type of trees named unrooted trees. So here you can see that here we cannot find the root of this tree. It's not obvious which one is the root. And this is also useful. We can exactly do the same things as I did for comparing species. This one for unrooted tree, it was very useful when you wanted to find exactly what's the parent. But here, when you describe your trees like that, it shows the distances, even distances between species. For example, if I want to find this species, the difference of this one with another, without even knowing about the root, I can see, for example, what's the path and what's the distance. Here in this unrooted tree, it was not sensitive to distances anyway, because if it was, for example, this line could be, for example, even longer to here. This one could be longer, this one may be shorter. So if it is sensitive to distances, it can give us very interesting information that, for example, unrooted tree couldn't give us. That's why it's important to know about both of them, about their differences, and try to apply it in different fields and different problems that we are trying to solve. Okay, guys, that was all for lecture 14. I hope this course was useful for you. I'm looking forward to receive your worthy solutions for the final. I wish you luck for all of your final exams. And I wish to see you guys also in the future courses in better times. If you have any questions, please let me know.